Welcome everybody to the Cretaceous carbonate part of this field trip. My name is Raffik Lazar and I will be your virtual field trip instructor. I'll bring you to the UAE. One quick word about Cretaceous. So it's coming from the Latin creta, which means chalk, and it's associated with a massive chalk deposit that we found mostly in the Western Europe. Cretaceous period itself ranges from 145 million years to 65 million years ago. At that time, climate was warmer than today. Fauna has colonized most of the Earth from the poles to the equator. There is a very infamous major extinction, which was probably related to the asteroid Winter, and that's how our friends, the dinosaurs, going extinct. In terms of paleogeography, the Pangea component started to drift at that time. Of course, the famous Tethys Ocean, which was separating land masses in the south and in the north. It's worth to note that the sea level was significantly higher than today. The Africa and South America were having their current shapes. If you were in India at that time, you probably will be living in an island. And then if you were in Australia, you will feel a little bit cold because you were still part of Antarctica. Cretaceous is always associated with the very famous redists. They come in all sorts of shapes, which is related to the paleobathymetry and the level of energy. In terms of the geological overview, so I'll bring you to the UAE in the Middle East. The environment is characterized by very shallow marine, what we call epieric platforms, which spans over hundreds of kilometers. And you also have a presence of intra-shelf basins, much shallower in terms of depth, and the CCD as well. So the depth where the carbonate are dissolved was significantly shallower than today. So today it's around 3,000 meters. At that time it was probably 50 to 100 meters. In those very big platforms, facies transition were very long. That's one thing. The second thing is that we are dealing mostly with biostroms. So as opposed to today, where or the tertiary, where we have reef building structures. So here it was contained within the layers, and we're talking about the typical fauna related to the redists and the corals. In terms of the stratigraphy, what we are going to see, the Cretaceous in the Middle East is split into three groups. The Thamama at the base, the Wasiya in the middle, and the Aruma. Most of the oil and gas field accumulations are in the Thamama and the Wasiya group. We are going to go to the northern part of the UAE, close to the tip of the peninsula and Strait of Hormuz in the Emirates of Ras Al Khaimah. We are going to focus on the Thamama group, so the Khwer, Kharaib and Shuaiba formations, and then we will have a look at the second stop in the Maudud and the Mishrif in the Wasiya. Stop number one, it's a place called Shimal, and thanks to the thrust and fall belt system related to the Zagros zone, the layers at that stop are basically vertical. So what will happen is we will just walk through the Thamama group from the base to the top part. The second step, we are going to look at something different. We are going to go to Rams. We will look at the Mishrif Maudud. We will go to an abandoned quarry, which I call the upscale cell outcrop, because the dimension of that quarry are roughly 100 by 100 meters, which is equal to a cell in a reservoir model. Thank you, and let's go. Alright, we are at the beginning of outcrop number one, so the locality of Shimal in Ras Al Khaimah. And what you are looking here is the base of the Cretaceous in white, which you can see here, and the top part of the Jurassic. We are going to zoom, we are going to get closer to the outcrop, and what you see exactly here, I'll pause, is this part of the sequence. So in white, it's the Thamama, which you can see here as well. Yeah, and then what you have in blue, these are conglomerates from the upper part of the Jurassic, and basically there have been an exposure of the platform at that time for a couple of million of years. That's why you have this unconformable surface. If I continue a little bit, you will see, if I zoom out slightly, you will see the unconformable nature of the surface, as you can see. So what we are going to do, we are going to move up in the sequence from here. So we are just going to turn around and walk through the younger part of the Thamama. Alright, getting closer now. So now we are somewhere in the Lechwer part of the Thamama. You will see these are mostly very muddy materials, non-reservoir. There are some beds where basically here, for example, where you have an accumulation of organism. These are probably condensed section, and it's very rare. The sequence is really dominated with mudstones. Yeah, you see the way it looks a bit closer. You still have parts of in blue. You can see here in blue, basically these are part of the Jurassic, so which means that at the earlier part of the Thamama, they are still been part of the platform, of the Jurassic platform, which have been exposed. So we are going to continue now. We also pay attention as well to the layering, to the joints in the formation, because it's quite interesting to see. Yeah. So we are moving up now into the sequence. So you can see you have those parts, if I'll just move a bit back, where you have limestone, massive limestone. You can see some stylolites, they will come again later. They are very characteristic of the Thamama. And then in between you have a part where there's screes, so these are probably intervals, slightly more shellier, and that correspond to the non-reservoir parts in the Thamama. Yeah, higher gamma ray as well. Then when you continue, you can see, I've been a bit too fast here, but you can see as well those alternations. You can see basically some cyclicity. So you have massive limestone of the Lechwer, then you start to see more stratification, then you have this throw in the middle, which is basically correspond to higher gamma ray values, and basically slightly more shale in the system. Yeah, and then the cyclicity start again. You have the same laminated stratified limestone, and then you go back into massive type of limestone. So we'll get a bit closer. Here I have superimposed a gamma ray and a porosity log from a well in Abu Dhabi. It's a bit far, but the principle is the same. So what you see, those stratification, those cyclicity, the throw probably corresponds where you have the gamma ray somewhere here in the middle, higher gamma ray, and then you get some cyclicity. You go back into massive limestone with probably better porosity. Those limestone in the lower part are mostly tight and not so good reservoir. You'll observe as well here, I'll make a stop, these are the nodules, silica nodules, which we call cherts, and they are related to the CCD. You remember I mentioned it. So basically the CCD was much shallower, and those cherts were probably sponges maybe that underwent some transformation due to the diagenesis. You remember I mentioned about stylolite and irregular bedding. This is very characteristic of the Thamama, and you can see also those mini sequences, 10 to 20 meters. That's exactly what you see on the subsurface, and then it's separated with a couple of meters of higher gamma ray. You will see as well the backside of this location, it's great. You can see the overturned layers and the stratigraphy, highly laminated. What is interesting is to see is the way those limestone they behave due to the weathering. So they are making those typical structures in honeycombs. Now, in the subsurface, do we have the same structures as well? You know, could that be the cause of karst, for example, and drilling losses? That's possible. All right, so here, something quite interesting is basically the expression of you have a shallowing up sequence. You can see here, and then there will be a sequence boundary. We are going to get closer, and then you will get a rapid gain in accommodation space, which will be translated in those laminated type of rocks, and then we'll get back to the cyclicity which we saw before. So let's get closer. So what happens is you will have a sequence with massive limestone, and then at the very top part you have these colors in purple, which is purple to brown, which is very typical of dolomitization. So what happened here, you had some exposure in the platform, and you have leaching and dolomitization. So of course what you see today has been enhanced by the weathering at the surface, but in the subsurface you pretty much see the same thing. Yeah. So that's the sequence boundary, and then what happened is you will see here if I stop. So that's the previous surfaces we saw. Yeah, you can still see the color, the dark color, which is related to the dolomitization and the exposure. And then you have a rapid gain in accommodation space, which is which translates into the alternation between centimeters thick mudstone beds in white, and then some intercalation of shallier, higher gamma ray interbeds. Yeah, and you can see that if I continue, if I move, you can see it clearly, the unconformable type of this boundary. Yeah, and you can see if you get closer to those type of reservoir, we'll just walk through it. There's basically no reservoir. You know, these are probably major baffles in the Thamama, and that's why it's a stack reservoir. We'll continue now. We'll go to the other side. Just wanted to show you as well. You also have those intervals where the stratification you see is irregular. It's like boudinage, and what it means at those locations, basically the layers, the carbonates are slightly more ductile, and that's again that shows that it's 100% mudstone, so there's virtually no porosity, and you will see when we'll go more to the younger part of the Thamama to the right, it will change. Here we start to see something different. Now we go into grainy material. You can see the way it looks, you know, very rough, coarser, much coarser than what we've seen before. So we'll continue, we move on. Here it's interesting, I wanted to show you as well some really short, very short scale sequences. Yeah, so you have a bed which is 20 centimeters, 30 centimeters, which is a bit darker, so probably a bit some of dolomite content. Then you have an irregular bedding, yeah, and then when you zoom in, you get back on the right, muddy material. I think you can distinguish little clast dark, but then you have these beds where you have a lot of shells. These are small redists which just come like that irregularly. Yeah. So what it shows that the system, you know, locally there are some vortex, you know, some movement, I mean, of sediment, and some little pools of energy. So here we are clearly in a Kharaib. The material is very different from the beginning. Here no more mudstones, big fossils, big clasts, coarser sediments. So here definitely a better reservoir. Yeah. We continue, we'll move up. Again here another sequence where it's made with a lot of redist shells. You can see them pretty much everywhere. So you have a very thick sediment package which is mostly dominated with the redist. So these are definitely much better reservoir. Yeah. So here again, just by looking at the appearance as well, you see very chalky. So that means that the properties are much better, and also the way it behaves due to the erosion as well and the weathering. We are in much better type of reservoir here. If I zoom in, you can see actually these are bioclast rich type of limestone. You can see here there are some algae and little fragments. Now here what I wanted to show you is again those redist. You can see they are really making thick bed, very solid, very compact. Yeah. One quick thing as well to see, in some of those intervals you have vugs as well, so some leaching of the limestone. That's important in the subsurface because that gives extra porosity and permeability. So again here we are just getting closer now, really closer to the top of the Thamama. So again I will make a pause, but you are basically in those bioclastic rich type of reservoir. Very good properties, and then that will be the end. Now here we are moving to outcrop number 2. We are in Rams, so the quarry, which basically we are jumping now in the Wasia, so the Mishrif Maudud, also known as the Natir in Oman. And this outcrop is interesting for two reasons, because it has exactly the dimension of an upscale cells in a model, so it's roughly 100 meters by 100 by 100, and you can see the 3 sides of it. And we'll get closer, you will see 2 interesting features. Very small scale clinoforms, which are very famous for this interval, Mishrif Maudud, and then also fractures. Fractures, you know, the way they behave in terms of the density and the length. So let's get closer. So we get closer now. The first thing I wanted to show you is, yeah, here we'll stop. You can see the clinoform, so the thickness will increase, will change laterally. You can see example here where the mouse is. You have probably a few centimeters, and as you move to the right, you can see the thickness is increasing compared to the previous stop on the Thamama. Actually, the reservoir is not as good as the Thamama, and on the flip side, it actually means that it tends to fracture more, and you can see there are definitely more fractures here as they extend all the way, and some are really contained within the beds. Yeah, you can see spacing as well, a couple of meters. Yeah. The last missing bits will be just to look at the lithology here. We're gonna have a look a bit closer. Let me get close, but basically here again very different if you compare to the Thamama. So here cementation, a bit more muddy, type of carbonates. If I zoom out a little bit, you will see as well some of the things we did not see, but you have a lot of marls in the system as well. You can see here, for example, this is a mudstone, which is 100% mudstone, though there is no porosity here, but then you can see it fractured. So fractures are really important. And then if I stop here, you will see as well there are marls, much more marls in the system than what we saw in the Thamama. Yeah. Some bioclast, some shells here, I think oysters. Again, oyster rich beds. So definitely shallow water type of environment. We'll conclude, you can see the layering. So here the key aspect is that within an upscale cells in the model, so 100 by 100 by 100, there are definitely some variations, And what I want you to take away is that a model at model scale, we have to make some simplification, at least on a lateral scale. Vertically, definitely depends on your layering, but you can still capture most of the heterogeneities. Yeah. All right. Thank you. I hope you enjoy.